Alright, so I've started the recording for this class. So we will basically pick up from where we left off. But before doing so, just a quick recap as to what we did the last time. We would have gone through the power switches, mainly the power MOSFET, the IGBT, the BJT, and GTO, and so on. We look at their characteristics, in particular the frequency at which they operate and the power, right, which are very important when it comes to selecting these devices for particular applications, right. We would have looked at a few scenarios, and from the scenarios you would have been able to to select appropriately the power switches for that application. Um, we will continue. All right, so these switches, you would have seen or noticed that they'll experience losses. Um, these losses can impact the efficiency of the device, right? So normally um, these switches, um, the losses have to be taken into consideration, primarily to ensure that the switch operates reliable under the prescribed ambient conditions, right? So the heat loss mechanisms, right? Normally, like heat sinks or radiators that are specified, um, will have to ensure to work in a way that will ensure that the heat is removed sufficiently from the device, and it works at the operating temperature, right? So that the efficiency is not compromised. We will review heat sinks. We look at the designs of these heat sinks later on in the course. The whole function of them is primarily to remove heat from systems. They can be large and bulky and expensive, and they will basically add to the overall cost of the system. Um, you will also see later on how we're actually able to cool the device sufficiently, um, so that they can operate at the specified junction temperature. Um, Important to note that if this cannot be realized, then we'll have to do what we call a derating of these switches, right? And you'd have seen earlier on that the main losses in these devices are from these three factors: the forward conduction losses, the blocking state losses, switching losses, right? These are the three main losses in your power switch, right? We would have looked at the profile of these switches and discuss them in detail. All right, so what I'm showing you here is just different types of heat sinks that you can have. We have our fin type in the top left hand corner, and here we have our SCR, and this is another type at the bottom that is used with the SCR, and the bottom right hand side, that's a power converter there, and you can see on it the heat sink that is attached to it. Right, so later on towards the end of the course we'll be studying the heat sinks in more detail, the design and so on. All right, the forward conduction loss. If you look on the top left hand side, that's an ID switch that is displayed, and the top right hand side we have a real switch. This could be your power MOSFET, your BJT, your IGBT, and so on. Right, so you would have seen that with the real switch, when this switch is turned on, the voltage drop across this switch ideally will be 0 volts. However, we'll have some amount of current that would be flowing through this switch. Right. However, our real switch, right, at turn on, there's some amount of voltage drop, right, that would be experienced. Right, normally about 1 to 3 volts, right, you would have when our real switches turn on. And important to note also is that the loss can be determined by the power of the voltage drop across the device, right, and the current that is flowing through the device. And of course, this is average over the period. All right, the blocking state loss. Right, so this type of loss, it occurs during turn off, and it will block large voltages. So when this switch is turning off, you will realize that you're going to have a large voltage across the switch, right? So this voltage is what is referred to as the blocking state voltage, right? And it results in the blocking state loss when we calculate the loss. Ideally, when a switch is turned off, there's no current that will flow, but you'll have what we call a leakage current that will be flowing in these devices at turn off, right? Very small amount of current, and this when multiplied by that voltage, that large voltage, will give us the blocking state loss. Of course, the leakage current that is experienced in the device at turn off is normally very, very small. So it's not a very large current that you will have flowing at turn off. So in most cases, this kind of loss can be neglected. What I'm showing you here It's basically the switching profile. So on the top right hand side, we have for the ideal case, sorry, the top left hand here, the ideal case, and the right hand side, that's the practical case. As you can see here, the device when it switches on and off, you can see instantaneous change in voltage and current, right, for the ideal case. However, this is not the case for real switches. There's some amount of time for the voltage to increase or decrease between turn on and turn off, right? The same for the current. When we look at this case, we have a high voltage initially as the device is turned off. As it goes from off to on here, we notice a very sharp change, right? Almost it's instantaneous between when the device turns off, between on and off, right? You'll recall we have the high voltage, right? So at this point, the device is turned off. It drops to 0 here, the device is turned off, right? So when the device is turned off, we don't have any current flowing through the device as is shown in the graph here. However, when it switches on, the voltage drops to 0, and in this case it's instantaneous. However, we have our current that will be flowing. So this ideal profile is showing us instantaneous transition between the on and off switches. However, for real switches, it's not the same. As you can see here, there's some delay between when the switch is turned on and turned off. You can see it's not instantaneous, right? The voltage gradually goes to 0. In the case of the current, it gradually rises as the device switches from off to on. So what we have here in the middle is the loss. And remember, we calculate the loss by simply taking the product of the voltage and the current, right? So you can see here we have a voltage at this point, we have a current that would be corresponding. So we can obtain the power loss here. So this would be the profile for a power loss, right? So as you can see, most of the loss occurs between on off, right? So we can summarize this result here, right? So say that it's doing the turn on and turn off, right? The ID switch will require 0 transition time. I have shown you that just now, and you have seen that the voltage and current switch is instantaneously. That was shown to you in the profile in the top left hand side. And also the power loss here would be 0 in the case of the ID switch, as you can see here, right? However, it's complete opposite that was shown here in the case of the real switch, right? So for this, right, the major loss is in the high frequency operation. Now, when we look at any power electronic device, in most cases we can find two terminals, right? That will allow for the current to flow through the device, and we'll have another terminal for the control of the device. And normally we have a drive circuit that is connected to that terminal, right? We would have looked at the whole concept of drivers earlier on in the course, right? So where we are able to use a small signal to control the device that is operating at a much higher voltage. Now, with this circuit, I'm going to demonstrate to you how devices can be protected from that high voltage that is experienced between when the device goes from on to off, right? There's a high voltage, right? There's also high current that will flow when the device goes from off to on, right? So I'll be going through that shortly with you. Let us analyze this circuit. I'm using, let us say I'm using this power switch here, and this is in a PCB. So we have here what we call the wire loops, right? So all of this is modeled as shown here. So let us use Kirchhoff's voltage law to analyze this circuit, right? So starting from this point, the V in, and we will go around this loop. So what do you have here? What's the voltage drop across the inductor? It's given by VL, right? So VL, and we now have a voltage drop across our power switch. In this case, let's say it is VCE. And as we come across here, do we have minus? This will be minus V in. And this is equal to 0. Right, so we have applied Kirchhoff's law around this closed loop. Right, so our V in here, right, is clearly equal to V to VL plus VCE. All right, now what is what is the voltage drop? How can we express the voltage drop across the inductor in terms of its inductance, right? You would have studied this when you did electrical circuits and networks, right? So this would just be equal to L di dt, right? Let me see. So we have a plus VCE, but we're interested in knowing how this is going to affect our VCE, right? So let me just rearrange, get a little space here. So our VCE, our VCE here would be equal to V in minus L di dt. Now look at this. When this part is changing, right, di dt is always going to be a negative, right? Because the change, because of Lenz's law, right, it will oppose the change. So therefore, what you have here, V in, is going to be V in plus, right? V in plus L di dt.
Can you repeat?
Because this part, di dt, right, with the inductor, when the current is decreasing, it is going to cause it to oppose this change. Are you following me?
Okay, sir.
Right. This is as a result of Lenz's law, right? So it will oppose the change. So when we switch, let's say from it's on, when we switch off, the current will tend to decrease, but the device is going to oppose this change, right? So this component will cause this to become positive because it's minus. So what you observe here is that there's a high voltage across the switch, right? VCE. There's a high voltage across the switch here. And this is what we need to protect the switch against, because it can damage the device. So that is demonstrated in this graph, right? So the device is switched off, right? There's a high voltage, it spikes up, right? VCE, and then it gradually goes towards steady state, right? So this, so yes,
What causes the spike?
what causes a spike? Remember what we have been showing here is that whenever devices switch from off to on or on to off, right, then you're going to have changes in the voltage and current. In the case of the real switch, when we switch from on to off, right, there's a high voltage across the switch.
Yeah.
Do you recall that?
Yes.
When we switch from on to off, there's a high voltage across the switch. However, there's no current that will be flowing through the device. Or we say just a very small current, the leakage current that will be flowing through the device in the real case. On the other hand, when the device switches from off to on, the voltage will go towards zero, right? For real devices, the voltage drop will be about 1 to 3 volts. However, we'll have a current that will be flowing through the switch. So what I've done here basically is a proof, right, to demonstrate this in a real switch, right, or power switch, right, a simple circuit that I've set up here, that I've modeled, right? So we'll have some amount of inductance in our wire, we have our power switch, and we have our power source here, right? So I was just showing to you what is happening, right? So we use Kirchhoff's voltage law here to write the equation in terms of voltage around the circuit, right? And then we make VCE the subject of the formula because we want to know what is the voltage across this device. We then analyze it, right? dR/dt, that's a change in current with respect to time. We know that because we have an inductor here, whenever there's a change, it is going to make this component negative, right? So minus minus makes the whole equation positive. So what we have realized is that there's going to be an overall increase in voltage across our switch, right? So that is why this transient curve is looking like this. So when the device switches from on to off, there's a high voltage that is seen across the switch initially, right? Because normally you would probably see just about the same voltage as the source. That's for ideal, right? But for real circuits, you'll have other things that will impact the overall voltage. As in this case, you can see the inductance in the circuit, right? So it's going to cause a spike in the voltage across the device. So this is not desirable, and so we have to protect our device. How do we protect it? I'm going to show you one method that we can use to protect our device, and this is the use of snubbers, right? So snubber devices can be employed to protect our device. And the one that we're going to study is what we call the RCD snubber, right? That's resistor, capacitor, and diode. That's what it is. So R resistor, C capacitor, and D diode. So that's all your snubber is going to be made up of, right? So it basically suppress that spike in voltage that I showed you earlier on. We don't want this spike. We don't want it. So with this snubber that you design, you'll be able to suppress, right, that spike that is observed. All right, so this spike, as I mentioned, can cause damage to the device. So that is why we have to design a circuit to suppress the sudden increase in voltage. All right, so what you're seeing here is a typical snubber across the device, right? So there's a circuit looking like this, made up of resistor, capacitor, and diode. All right, so when this snubber is introduced, if you recall earlier on, without the snubber, we have these oscillations, right? The high spike and then the gradual steady state. With the snubber, as you can see here, it's a smoother transition. We don't have that spike that will cause damage to your device. So it basically dampens the effect of the high voltage right? So it keeps it at a safe level. All right. So I'll summarize, right, what we use snubbers for. As I can see, when we turn on, we need to be able to minimize that over current through the device. When we turn off, there's the over voltage that comes into place. We need to be able to protect the device from that. Also, there's what we call stress reduction, basically shaping the waveform that we observe for the voltage and the current, ensuring that we don't have them spiking at the same time, right? So that's what we refer to as stress reduction. It's important here to note that the switches, like the IGBT, the MOSFET, and the IGCT, basically the newer type of devices, we don't need to use snubber for them. Most of them has built-in protection, right? So it's devices like diodes and some switches that will require the use of snubbers. So what I'm showing you here is a snubber that we will study, right? So it has inductor, it has capacitance, right, and a resistor here. We're going to protect this diode, and we'll use this formula to determine the capacitance that we'll use, right? So we have capacitance is given by the value of inductance multiplied by the square of the recovery current divided by the product of the voltage and the optimum current factor. I will explain these in a worked example shortly. Also, how do we calculate this resistance? It's given by this expression. Here we have 2 times what called the optimum damping factor, given by this little symbol here, sigma, multiplied by the square root of the inductance divided by the capacitance. So these are the formulas that I expect you to be able to use to determine the elements in this snubber that we will be studying. All right, so this is the graph that you'll actually be using to obtain the components of your snubber. Let me. All right, so here's a question. All right, so the recovery current of a diode as shown in figure 2. This is the figure that we're talking about. Right, is IR equal 20 amperes, and the circuit inductance is L equal 50 microhenry. The input voltage, that's Vs, is 220 volts, It is necessary to limit the peak transient voltage to 1.5 times the input voltage. You are now asked to determine the optimum value of current factor D0, optimum damping factor sigma naught, the snubber capacitance, and the snubber resistance. Right, this is very simple. You will just be using the formula to do this calculation. All right, let me make some space here. All right, so we will go through this one together. All right, so the first question, it asks us to determine the optimum current factor here. Let me just write down the expressions that.
So
Yes.
can I get a minute to just write down the values?
Pardon me?
Can we get a minute to just write down the values?
Oh, sure, right. And take down these formulas as well. Or you with the circuit, draw the circuit, and the formula that you'll be using to determine the values of the circuit. So take this circuit down as well as the formula. Finish?
Yes, sir. Can I move on to the values?
All right. Right. The question. All right. So that's the question.
Oh, 1 second.
All right. Okay. All right. So, are you finished?
Yes, sir.
All right. So basically, we will need those formulas, right, for the capacitance, right? So we can extract the information. So your formula for capacitance. Oh, sorry. You see, don't know what happened here. I just fix this problem. All right. So C equal L. All of this into the reverse recovery current divided by D naught times your input voltage, right? Vs all square. And of course, for your inductance, sorry, your resistance, but R is equal to 2 times the sigma square root of L over C. All right, so from the question, you're told that the input, let me see, the input voltage Vs, that's 220 volts, and that it is necessary to limit the peak transient voltage to 1.5 times the input voltage. Right, so your input voltage Vs, that's equal to 220 volts, and that expression, right? So how can we write this information down where it says it is necessary to limit the peak transient voltage to 1.5 times the input voltage? What that is saying, the peak transient should be equal to 1.5 times the input voltage Vs. Right? So in other words, the ratio of the peak transient voltage to the input voltage, right? And this peak transient voltage is what we're referring to when the device is turned off. When it turns off, you don't want it to rise above 1.5 times the input voltage, right? That is what it's saying. You want to constrain it, you want to suppress it, right? At this level, right? Should not exceed that. So the ratio VP to VS, that's 1.5. Now, how are you going to use this? All right, so in doing the calculation, we need to find out what the value D naught is equal to, right? So D naught being the optimum current factor. How do we calculate that optimum current factor? We're going to use a graph, right? We're going to use a graph to determine our value of D naught, right? So here's the graph. Sorry, the graph is here. All right, so looking at this graph, we see one curve that gives the ratio of the peak transient voltage to the input voltage, right? So this is a curve. And we also have another curve here that gives us the sigma naught, that is the optimum damping factor, right? So sigma naught, optimum damping factor. All right, so how do we get D naught? From this graph, you will locate where VP to VS, that's the repeat voltage to the input voltage. Where is it equal to 1.5? So you look on the x-axis, sorry, the y-axis, we have 1 here. So 1.5 is somewhere here. You go across, right? And you hit the VP to VS curve. And then you come all the way down to get your D naught, your initial current factor, D naught. When it's time for your sigma, right, you will hit that sigma naught curve and you go across and read off your value. All right, so from this graph, I want you to tell me what D naught is equal to, right? For a ratio of VP to VS, that's peak voltage to input voltage of 1.5. What would be the initial current factor?
0.7, sir.
All right, yes, that's about 0.7, right? So 1.5 come across, then you come down and it's about 0.7. All right, so we can start working this one out. So the C, right? You know that from the graph, your D naught is equal to 0.7. So you're going to now substitute. What is our value of inductor? It says 50 microhenry, right? So 50 times 10 to the minus 6. And IR, the reverse recovery current, you're told that it's 20 amperes. So you substitute 20 here. And your D naught, you'd have obtained it from your graph. So that's 0.7 multiplied by, oops, sorry, here. Let me get that line out. 20. So that's 0.7, and your input voltage is 220. Can work that out. What do you get?
Sir, I get 84.33.
I got 1 microfarad.
Why so many different answers? 1 microfarad, 84 point something. What is the what is the right answer?
I get 84.
Yeah,
84 microfarad.
84.
84.
That's now 3 answers. That's very strange. 3 different answers.
I work it back on my side.
I thought this was a simple exercise.
Yes, sir, I got 84,
Huh?
84.3 microfarad.
Microfarad.
Yes, sir, that's it.
Right here. I thought this was a simple exercise. So many different answers.
Oh, I had 200 instead of 220 in the calculator. It's 84.3.
Don't worry, it always happens. So you're saying
But
this is what?
but it's actually 0.8 microfarad.
0.84
Yeah.
microfarad,
0.84.
right? Oh boy, this always happens, right? So now we can calculate our R, right? So it's 2 times sigma. But what is sigma? You'll have to and calculate your sigma from the graph. So again, 1.5 come across, come down, and hit the sigma curve. Then you go across and read off your value. What do you get?
It's about
0.45.
0.45.
0.45.
0.45.
Yeah.
Okay. All right. All right. As long as you don't get anything like 0.6 or 0.8 or 0.2, anything near 0.4 is okay. All right. So let's use sigma. You said 0.
There's a lot of noise.
There's a noise in the background, so I'm not sure.
Oh, whose phone is on?
Oh, it's gone now.
Okay.
So you can repeat, how did you find the sigma?
hold on, let me get back this up. How to find sigma? All right. You know the ratio of the peak voltage to the input voltage, right? That's 1.5. So you locate that 1.5 and you come across, right? So to get the sigma, you'll have to come all the way down to the sigma curve, right? And wherever you hit that curve, you'll go across and read off this value that you obtain on the y-axis here, and that will be your sigma. So in this case, 1.5 would be about somewhere here. You go across, so that's the ratio, and then you come down, you hit the sigma curve, and then you go across, and the value we get is about 0.4. So I guess some persons got 0.5, but that's okay. All right. So if you get 0.4, 0.45, that's all right. As long as you're not getting 0.6, that would be way out. 0.8, 0.2, that would be way off. Right. So we can work with anything in the vicinity of 0.4. Right. So I think you gave me the value of 0.45, right, a short while ago. So we work with 0.45. And so it's a matter of now substituting these values into the expression. So R is 2 times sigma, that's 0.45, right? And your L, that was given to you, your L, that is 50 microhenry, right? So 50, this thing, yeah, 50 microhenry divided by C, and your value of capacitance here, you would have calculated it just now. So it is 0.84. Well, I hope you don't tell me different answers now. All right, what do you get?
Six point nine four.
6.94.
6.94 times 10 to the minus 3.
All right, so that's about
To the minus 3.
what's
It's just 6.94.
right, 6.94 ohms, right? Right, so it's about 7 ohms, right? So I'm hearing different answers again.
Times 10 to the minus 3, sir.
I think that one is wrong.
No man, no minus 3 no different.
That one is wrong. It's just about 7 ohms. You have to check again. Maybe you press something on your calculator, or your calculator is just malfunctioning. All right, so that's how we will calculate the values for our snubber, right? This is the one that we'll study for this course. Right? Very simple. Right, so I have a slide here. We just summarize our ideal switch and our practical switch. All right. Just before we conclude this lesson, so we have seen that the ideal, right? When we're switching from on to off, there's a large voltage. There's a large voltage that would be across the switch. Large voltage. However, in practical switches, the voltage is fixed, right? It's not zero, right? It's a fixed amount of voltage drop that you will observe when the switches go from off to on, right? For the ideal switch, there will be 0 volts, but for practical switches, right, it's about 1 to 3 volts that will be observed in the device. Of course, when it goes from off to on, normally you will observe that you'll have a current flow, right? While you have a voltage drop of about 1 to 3 volts. In the case of like IGBT, it's 2 to 3 volts, right? On the other hand, you don't have any voltage drop in going from off to on in the ideal switch, right? And you have 0 voltage drop. The switch, as we have seen earlier on, when we go from on to off or from off to on, right? It's instantaneous. But for our real switches, when we go from on to off or off to on, this time is not instantaneous. It takes some amount of time, as you would have seen with the profile of the switch, that IV profile that I show you of the switch. Also, you would have seen that we can use a very small power to control a much larger voltage or current in a power switch, right? That's for the ideal switch, right? But with these practical switches, you're going to need some kind of a driver, right? There's a driver that we normally use to trigger these devices, and they require much larger current, right, for the switching in the case of the GTO. Now in the case of the IGBT and the MOSFET, these are what we call voltage control devices, right? So they'll require small power to trigger them. All right, so this part of the lesson is finished. All right, so All right, I'm going to